Thank you so much for inviting me to the workshop, and thank you for hosting this really great set of talks. Can everyone hear me okay and see slides? Excellent. So this is joint work with Daniel Hauser, and I'm going to give sort of an overview talk to motivate the topic and try and highlight most of the results through the lens of a couple examples, just since I only have 25 minutes and therefore it's not quite enough time to get into all of the technical details. So if you have any questions, happy to chat more about it after as well. So if we look at classic learning models, when agents are learning about the world, they're incorporating information from a variety of diverse sources. And there's a large empirical literature in psychology and economics that documents failures of statistical reasoning in different contexts and ways in which agents distort information. So for example, failure to account for correlation, failure to properly interpret signals in terms of their precision, something like overconfidence, motivated reasoning, which causes agents to systematically slant information in a particular direction. And so how as economists have we modeled this? Well, there's been two different key approaches. Both approaches assume that agents are expected utility maximizers, but update their beliefs correctly in some way. The first approach is an area that's close to my heart. I have a lot of other work in this area, and this is looking at the model misspecification approach, which says that an agent has a model of the world. They use this model to interpret signals, whatever the signal is, be it a private signal, other agents' actions, so on and so forth. They form beliefs using Bayes' rule with respect to this model, but their model may be wrong. So they may have an incorrect model of the world. For example, believing distributions are independent when they're actually correlated. In contrast, the approach we've seen a bit more in the behavioral theory literature is what we call the heuristic approach. And this is just an arbitrary function that maps signals and prior beliefs to posterior beliefs for the agent. So you could just think you take a signal, and then your heuristic will tell you what belief the agent will have from that signal. And so each of these approaches has different advantages. The goal of this talk is going to be to link these two approaches and see when they're similar and see when they're different. So first, for the model misspecification approach, why would we use this approach? Why is this a valuable approach? Well, first of all, as been illustrated in the many papers in this area, it can capture a variety of behavioral biases without departing too far from the standard framework. So what do I mean by the standard framework? Agents have a correct model and update using Bayes' rule with respect to that correct model. Here, we're relaxing the assumption that the model is correct, but we are still maintaining Bayes' rule, which gives us a lot of analytical tractability in terms of studying the implications of learning in this setting. It's also been shown to help construct interesting examples or models. Again, the structure has a lot of structure, and so it really helps us sort of write down different ways that we could think about agents making learning errors. And then lastly, if our core questions are thinking about how such learning biases may impact, say, markets or different classic economic questions, then it's a lot easier to embed the model misspecification framework in existing other frameworks. So say take it to a market for looking at how prices are determined or something like that, than say using some arbitrary heuristic. And so this approach, as you can see, has many advantages. There's been a rich literature, especially recently with economics, studying different types of results with model misspecification. So going back to the classic statistics literature, what do we know so far? Well, Brook back in 1966 showed us that for well-behaved, in quotes, data, the asymptotic results are that agents' beliefs are going to converge to the closest model to the truth. So if the truth is not in the support of their models, they're going to converge to whichever model is the closest. This can lead to something like incorrect learning if, say, the model in a given incorrect state is closer to the true model in the correct state than the misspecified model in the correct state. Also, recently, there's been work looking at how to extend equilibrium concepts to model misspecification. By now, probably most people are familiar with the Burke-Nash equilibrium, which is a solution concept developed in Esponda Puzo, and looks at equilibrium for misspecified models. It nests many standard other behavioral solution concepts, such as analogy-based expectation equilibrium and cursed equilibrium. And then lastly, a recent literature in economics, including my work and Other work by Mira Frick, Yuichi Yamamoto, Esponda, Puzo, many other people. I didn't put all the citations because there's a lot of recent papers, look at the asymptotics of misspecified learning and conditions for convergence to Berg-Nash equilibrium. So this has been a relatively active area of research within economics, especially more recently. Whereas in contrast, if we look at the heuristics approach, well, why would we want to use this approach? Well, it also does have some advantages. First of all, it more transparently captures the conceptual interpretation of a distortion. So if you want to say something like agents have partisan bias, in other words, they slant all of their information towards one of the states, for example, certain newspapers slant liberal or Republican, it's a lot easier to quote unquote see that that's what's going on with the misspecified, or see that's what's going on with the bias when it's written as a heuristic rather than when it's written as some sort of underlying distribution over signals. It's also easier to capture the specific way in which agents distort signals. So you can think of a heuristic as more akin to what might actually be in somebody's head. For example, they're counting signals twice, they're overreacting, they're counting signals twice, or they're having motivated reasoning, they're miscoding certain signals. If they do poorly on a test, they're justifying it as I had a bad day rather than I'm not very smart. So it's conceptually a bit more compelling. And also it's easier to, if we wanted to then take it to the data, it'd be easier to identify from choice data because you can provide agents with information and then elicit beliefs. What do we know from this literature? Well, really what we have is a series of case-by-case results for how specific heuristics impact learning. In other words, someone will write down a heuristic. For example, Rabin and Schrag wrote down a heuristic for confirmation bias, over-interpreting information that confirms your prior. Epstein nor Sandroni wrote one down for under or overreaction, and then they derived for that specific function, what are the long-run impacts for learning? And so this contrasts with the model misspecification approach, which provides a general framework and a general set of results. So we don't need to, for each new misspecified model, figure out the new asymptotic implications. We have a general framework, but it also gives us little guidance on how to model specific biases. And therefore, that's where the heuristic approach can come in useful. So the goal of this paper is to connect the two approaches. And the key questions we ask are, first of all, is it possible to represent a heuristic as a misspecified model and vice versa? In other words, if we take a heuristic, does there exist a misspecified model that leads to the same pattern of beliefs across time when agents are learning, and similarly for the other direction? And then second of all, are there multiple misspecified models that represent a heuristic? Turns out yes. And given that there are, which one should we be used? So essentially, if we take a conceptually compelling heuristic and we want to represent it as a misspecified model to then do analysis in a market, doesn't matter which of those multiple models we choose in order to do this analysis. Okay, so I'm going to look at a really simple setup for the talk. There's two states of the world, state omega, either L or R. In the paper, we look at an arbitrary finite number of states. There's some prior belief P that the state is R, and the agent learns from some signal drawn from a signal space with CDF, state contingent CDF, F of S conditional on omega, and PDF, lowercase f of S conditional on omega. And so we're going to be agnostic about what this signal can be. It could be a private signal an agent's observing. It could be another agent's outcome. If they studied, did they pass the test? It could be another agent's action choice. Did they choose to invest in their 401k? So something like a social learning framework. We're just going to say there's some given information that the agent's learning from. We're going to assume that in the correct model, the signal is informative. So in other words, the distributions differ across the states. And we're going to normalize the signal to be the posterior belief that the state is R, conditional on that signal. And so we can denote the support by a subset of the posterior belief space in this simple two-state framework. All right, so how would we capture a misspecified model? This is pretty standard in the misspecified literature. Here, the misspecified model, the agent's model of the world is their belief about the signal distributions in each state. And we denote these perceived signal distributions by uppercase F hat for the CDF, lowercase f hat for the PDF. And model misspecification captures the idea that these subjective or perceived signal distributions may differ from the true underlying distributions. We maintain one assumption for just sort of a technical condition. We assume that the perceived distributions are mutually absolutely continuous with respect to the true model. So in other words, agents aren't seeing signals that they don't expect, that they would expect with probability 0 in the true model. And also we assume that agents believe the signals are informative, otherwise they don't learn, and so it's not interesting. Now with this misspecified model, agents use Bayes' rule to update their belief after observing some signal S. And so their posterior belief that the state is R conditional on the signal S, again, using the hat notation to denote the agent's belief rather than the correct belief, is just simply we're applying Bayes' rule to the perceived signal distributions. One more little piece of notation. This isn't going to come in to play until a little bit further down the road in the talk, but we can also think about the agent's perceived belief about their posterior belief, the perceived distribution of their posterior belief. And so if we let S hat denote the agent's posterior, given their model of the world, then we let F hat of S hat denote the agent's perceived distribution of what their posterior belief could be. And so this is going to come into play later on when we're trying to figure out which model may make sense. It turns out there's a compelling condition on the agent's perceived posterior belief in terms of how they're forecasting future beliefs that we may want to sometimes incorporate. So more on that later. Okay, whereas the setup for the heuristic is simply a function h that maps signals and prior beliefs to posterior beliefs. So it maps each signal realization to the posterior, again, using hat to denote the subjective posterior that the state is R, conditional on seeing signal S. And the running example of the heuristic that I'm going to use throughout the paper is a form of overconfidence, in particular overprecision, in which agents believe that the signal is more precise than it actually is. So they're essentially behaving as if they say count the signal 2 or 3 times, like they've seen it 2 or 3 times when they're forming their beliefs. We could write out such a heuristic as this function right here, where nu greater than 1 captures the level of overprecision, higher nu corresponds to more overprecision, nu is equal to 1 is the case of correctly interpreting signals. All right, so any questions on this before I move forward? I'm also happy to take questions at the end since I don't have a lot of time. All right, so the first result is kind of essentially it's an anything goes result, and it's relatively obvious from results that are already out there, building on work that's already out there. But our first result is what we call the representation that links heuristics and misspecified models. And so we show that any heuristic can be represented by a prior dependent family of misspecified models. What prior dependent means is that that misspecified model may vary with the current belief the agent has about the state. It doesn't necessarily stay the same across all beliefs. If and only if the prior belief is in S of P, where S of P is the relative interior of the convex hull of the heuristic. All right, so that seems a little bit technical. Let me just quickly discuss the intuition for it. So first of all, this is a generalization of work by Shmaya and Yariv, looking at when we can really use Bayes' rule with respect, it's a generalization with respect to the signal space that we look at. And the basic intuition is that Bayes' rule requires the martingale property to hold with respect to the posterior. In other words, the expected value of your posterior needs to be equal to the prior. And so the heuristic must be such that it allows this to be feasible. What does it rule out? Well, it rules out something where, say, your prior belief is that each state is equally likely, but after every signal in the support, you then come to think that the state is R with, say, probability 0.9 or somewhere above 0.5. In other words, every signal moves your belief up above your prior. The second is just the other direction. Any family of mutually absolutely continuous misspecified models can induce a heuristic, induces a heuristic. And so this is basically just Bayes' rule. The heuristic for a family of models is just taking Bayes' rule to map, using Bayes' rule to map signals and priors to posteriors. So what do we learn from this result? Well, we learned that basically anything goes. It's easy to find at least one misspecified model that represents the heuristic. More interestingly, we want to see whether is this model unique, or what can we say about different classes of models that could represent heuristics. Oh, one other thing I wanted to point out before moving on to the next result is that this prior dependent result, the fact that you need a prior dependent family of misspecified models, we can get rid of that dependence if and only if the signal distortion in the heuristic doesn't depend on the prior. The formal condition means that if we take the likelihood ratio of state R to state L from the heuristic and multiply it by the inverse of P over 1 minus P, so probability of L over R, then we're gonna be left with something that's independent of the prior. And this is satisfied in some compelling examples. It's satisfied in our overprecision example. We're left with S over 1 minus S to the nu if we do this, but it's also not satisfied in many interesting classes of misspecified models that are heuristics that have been looked at in the literature. Okay, so the next thing we have is, which speaks to the question of what misspecified models can represent a heuristic, and also, do we have to worry about multiplicity? So given a heuristic in a family of unconditional misspecified distributions, the unconditional misspecified distribution is just the expectation of each conditional misspecified distribution with beliefs, then the heuristic can be represented by this model if for each prior, the expectation of the belief from the heuristic is equal to the prior. So this is really the analog of Bayes' plausibility with respect to the heuristic. Essentially, any misspecified distribution that satisfies this analog can actually be used to represent the heuristic. So Bayes' plausibility isn't going to place any further restrictions on which families of misspecified distributions can represent a given heuristic. However, once we do have the unconditional misspecified distribution, then it's going to exactly pin down the conditional distributions in each state. And we could also go the other direction. We could start with, say, if we write out a conditional distribution in state R, then this is going to fully pin down the conditional distribution in state L and the unconditional distribution that could represent a given heuristic, and vice versa. So each unconditional distribution is either going to be incompatible with the heuristic, it doesn't satisfy Bayes' plausibility, or it's going to uniquely determine the entire model. And similarly, if we say started with a conditional distribution in one of the states. And then lastly, as you can see, as you can see from this condition, there's going to, in general, be many unconditional misspecified distributions that will satisfy this condition. And therefore, in general, there's going to be a multiplicity of misspecified models that can represent a given heuristic. So just starting with a heuristic, we can't then use our representation to say, all right, well, here now we have a unique misspecified model that we can work with that's going to let us analyze the implications of the heuristic. So the first question you might ask is, does this matter? Well, here we're going to look at, does it matter for asymptotics? In other words, if we say, look at different misspecified distributions that represent a given heuristic, do we make the same predictions for asymptotic learning, or do we end up with different predictions for different models? Let's first look at a super simple case where agents just learn from a sequence of conditionally IID signals and see what happens in the long run. So for IID learning like this, Burke's 1967 theorem tells us that beliefs are going to converge to the state that minimizes the relative entropy from the truth. In other words, if the true state is R, then beliefs will converge to the state that minimizes the difference between the subjective signal distribution F hat in that state and this true distribution in state R. All right, so in the overprecision example, we actually get a pretty stark result. We see that there's going to be correct learning independent of the choice of misspecified model to represent the heuristic. I'm not going to go through the proof since I don't have a lot of time left, but it really just sort of pops directly out of this construction of the relative entropy expression. We see that plugging in whichever model we choose, it's just going to reduce to something that only depends on the heuristic, not the chosen misspecified model. And also it's going to give us a condition where the true model is closest, the subjective belief in the true model is, or in the true state is closest to the true model in the true state.
And can I ask a clarifying question quickly?
Yeah.
If it's okay. I must be a little bit confused maybe, but it seems to imply that specifying a heuristic doesn't sort of close the model, right? If it's been a meaningful question, whether different misspecified models that represent a heuristic give different answers, it means that the heuristic itself doesn't fully specify what the model is. And I don't quite see why. Because I thought the heuristic already specifies how the agent is going to update and behave.
So that's a great way of putting it. You're exactly right that the multiple misspecified models can represent the same heuristic. So I'm actually, after this, I'm going to give you an example where it doesn't hold, and that might help give a little more intuition for why it's not obvious. But sort of intuitive.
May I jump in here?
Sure.
I think, Piotr, maybe because it ignores beliefs over beliefs. So it just gives first order beliefs, and we know things depend sometimes on higher order beliefs. Would that be the reason that heuristics is not enough?
So it depends on it depends on how a heuristic you could think of like picking a given, the heuristic we're specifying on a given, mapping a given signal to a posterior belief. But if we embed that, so one example I'm going to have here, which is going to show that if we say now embed this heuristic in a social learning model, then there's going to be details of the environment that are not just pinned down by that heuristic. And so in that case, then we're not going to have this nice property where we're just looking at this ratio here, which essentially reduces to the heuristic. It's also going to depend on the agent's beliefs about how other agents are updated. So that would be one case. There are potentially individual learning cases where we could also not have this hold. So a lot of the cases that we're interested in economics is what I call endogenous learning, or what the literature calls endogenous learning. And that's when the information that's being generated is going to vary across time based on, say, action choices. So you can think about social learning. The information generated depends on other agents' action choices. Something like a bandit problem, the information generated depends on the choice of the arm that you're experimenting with.
Just 5 minutes.
Okay, 5 minutes. So let me keep going, and then I'm happy to stay on after for additional questions. Okay, so is the learning outcome always independent of the choice of the misspecified model? It turns out it's no. I constructed an example to illustrate this. Let me just give a brief overview of the details so I can get to the other results that we have. And so basically, if we embed this overprecision example in a sequential social learning game, where a sequence of agents are acting, and each agent T at time T observes a private signal and then chooses some action, we can show that, and then agents are learning from other agents' action. I'm just going to skip the details here, but basically once agents are learning from other agents' actions, they both need a model of the signal process as well as the model of how other agents learn. We look at a really simple case here where agents have a correct, agents essentially have the belief that all other agents are the same as them or using the same model. And from a characterization and other work I have with Daniel, in this setting, or we have a general framework for analyzing asymptotic learning in this setting with endogenous information. It's endogenous because the informativeness of action choices depend on the history. And here, asymptotic beliefs are fully characterized by an expression that's analogous to the relative entropy at certain beliefs. So at either thinking the state is R with probability 1 or thinking the state is L with probability 1. And so from this construction, we can see that the chosen model, F hat, is going to matter for the asymptotics. Specifically, this expression here, which is going to determine the set of asymptotic beliefs, is going to depend on our choice of model. So this here is the relative probability of the action in each state at a given prior, these psi hats. And the ratio of these psi hats in each state, unlike the previous case where we're looking at individual learning, is going to depend on our underlying model. What that means is that different models are going to potentially lead to different sets, lambda of omega. We show that in fact they do in this overprecision example. And therefore different sets of stable beliefs are going to lead to different asymptotic learning predictions. So this was just a simple example to illustrate it, but more broadly, the takeaway is that for heuristics, there are going to be settings where the choice of the specified model is going to matter for what the long-run learning outcome is. And so we might say, well, now what if we want to look at this connection between heuristics and misspecified models? Are there natural restrictions, or is there a way to select which misspecified model is the most compelling one to choose? We have proposed 2 natural restrictions on the set of misspecified models that can be used to represent a given heuristic. Each of them leads to different desirable properties, as well as a unique representation. So the first is unawareness. Misspecified agents and correctly specified agents have the same forecasts over future beliefs. And so this is natural if you look to the behavioral literature. Often biases are thought of as something that people have at the time when they make the decision, but they're not aware of it. So they think that in the future, they're going to be making correct predictions and correctly interpreting information. So something like the self-control literature. But in fact, when they actually come to that decision point, they are using this heuristic, which leads them to incorrectly interpret information. Whereas in contrast, we could think of something that we call introspection proof. And this is really taking the misspecified model seriously, saying, what if people are just, they're not really sure what the model of the world is, but they're constantly looking at the data they've seen in the past and inspecting it to see, am I observing data that's consistent with my model, or am I seeing something that really is unlikely? And so one of the criticisms of the model misspecification literature is that in certain applications of it, people are going to essentially asymptotically be seeing events that they place probability 0 on. And so, why doesn't that trigger, say, an introspection or a realization that your model is wrong? And so what introspection proof tells us is that even with infinite data, you have no reason to doubt your model. In other words, your expected model is exactly equal to what you're seeing. So both of these we can think about in a simple diagram relating the different distributions. And both of these restrictions are going to be using the correctly specified model to impose some structure on the misspecified model. So here we have a simple diagram. We have the conditional distribution in each state. This is the true distribution. This is the subjective distribution. And remember the piece of notation from before, this is the agent's subjective belief about their posterior distribution. Our heuristic is giving us a mapping between these two. What does unawareness give us? Well, it tells us that the true distribution over the true posterior is equal to the agent's subjective distribution over the subjective posterior. So it's saying that these two are identical. In other words, agents are making the same forecasts over their beliefs as correctly specified agents. Whereas introspection proof now, what's relevant when the agent's looking at their past data is their current expectation of that, which is their expected belief about the signals given their current belief about the state. This is the unconditional signal distribution. And introspection proof tells us that the actual unconditional signal distribution is equal to the subjective signal distribution. So agents are not seeing anything that's inconsistent with their model when they look back at past data to think about whether their model makes sense. All right, so I'm just about out of time, so I'm just going to quickly go through the two results. As I already described, unawareness, essentially our result for this is conditions on the heuristic and the misspecified model such that we can find an unawareness representation. And so essentially for any measurable one-to-one heuristic H with measurable inverse, an unaware misspecified model exists if the heuristic maps measure 0 sets to measure 0 sets. Moreover, this unaware misspecified model is unique. All right, so just to give a little interpretation in the overprecision example, here we're assuming that agents over underweight private information, they're not accounting for the fact that others do the same. And so they're interpreting actions as if they come from an unbiased decision maker, but they are evaluating new signals using their heuristic. So this does have a unawareness representation. Moreover, when there is an unawareness representation, it's going to be unique. So this will really pin down a unique mapping from the heuristic to the misspecified model. Our results for introspection are similar. I didn't write them out since I figured I'd be out of time by around now. But essentially we have a condition for representation by an introspection proof model, as well as a result that shows that if such a representation exists, then again, it's unique. So it's going to uniquely pin down the specific misspecified model that represents the heuristic and satisfies introspection proofness. So what are the key takeaways? Many heuristics can be represented as misspecified models. This is good news because we can use off-the-shelf results from a more tractable analytical framework to analyze these heuristics. But it's bad news because there's a multiplicity and therefore too much flexibility in modeling. And then we examine two interesting classes of misspecified models and show that these actually uniquely pin down misspecified mapping from the heuristics to misspecified model. And so they give us more structure in terms of how to use misspecified models to capture these heuristics. All right, so I'll stop here. Thanks for coming and happy to take any questions.
Thank you, Aislinn. Any questions?
Yeah, I have one question. I'm not sure I fully follow the last part, but is unawareness a good criterion for just discussing misspecified models, even without the context of heuristics? Or is it because I didn't completely follow whether the criterion depends on the heuristics or it's a consistency requirement for misspecified models?
So I think they're both unawareness and introspection proof are properties of misspecified models that you could just, if you didn't want to start with a heuristic, you could say you're starting with misspecified models, the compelling property, and either use unawareness or introspection proof.
So they have their own merit independently of the connection between heuristics and misspecified models. You're just saying if you use misspecified models for whatever reason, either to capture heuristics or not, it doesn't matter. You should be thinking about misspecified models which have an extra property.
Yeah, I mean, depending on the context you're looking at, you may want to use, so introspection proof is something that's been discussed a bit in the literature in terms of, will agents see zero probability events if they have this model versus will they not? Some models out there satisfy it, or some papers out there maintain it, some don't. Unawareness is relatively more novel, but again, both of them are properties that you could just say, I'm going to start with a misspecified model. This is conceptually what I'm trying to capture. And I think in this conceptual setting, unawareness is a compelling property to have. So I would argue unawareness is compelling for settings like self-control problems or other settings where agents are naive about their bias, whatever conceptual bias you're capturing. Whereas introspection proof may be more applicable for settings like, for example, if you're thinking about scientific reasoning and you think people are really, their goal is they know they might have a wrong model. They're just not sure where to start, or they need to simplify the world so they have some model, but they're constantly questioning their model and looking at data and saying, do I have a more compelling alternative model that I could be using? And in which case, if the answer is yes, if the model is not introspection proof, then this misspecified model may not survive. Whereas if the answer is no, then it could be that the misspecified model survives, even if the the correct model is out there and the agent has it in the back of their head as well.
Thank you. Thanks.
Thank you, Aislinn.
There's a question in the chat as well, I think, and it's about the first theorem you showed us, the representation theorem. Does the representation theorem imply difficulty or nearly impossibility of identifying whether a subject is non-Bayesian or Bayesian with misspecified model, say in an experimental study?
No, because if if you're say doing an experimental study where you can exactly control the distribution, then you can take a look at what the Bayesian beliefs should be. And if their elicited beliefs are different, then you would be able to identify whether they were non-Bayesian. I'm just reading the question again. Oh, is it from separating whether an agent is non-Bayesian or Bayesian with a misspecified model, rather than separating whether an agent is Bayesian or yeah, so I think in terms of separating whether an agent is non-Bayesian, so in other words, uses a heuristic is what I would call that setting, or is updating using Bayes' rule, but with a misspecified model. really the whole paper is really pointing at the fact that these two are essentially pretty similar approaches. So because we can represent non-Bayesian agents as Bayesian agents with misspecified models, as long as they're, the patterns or their beliefs are the same, that's really not something we'd be able to identify. What the model is in their head in terms of how they're forming their beliefs.
Well,
So the only way you could separate that would be the case where you have a, say, heuristic that